In this video, we want to explore direct variation and connect it to notions of ratio that we've already seen so far in Mat 150. So if I look over here, I want to first talk informally about what I'm talking about with direct variation. I'm talking here about pounds of candy, that's one variable, and another variable, cost. So we can see just very informally as the number of pounds increases, so as we buy more and more pounds, the cost is going to increase. And that makes sense. So that's just kind of an informal, if one thing goes up, then the other one is going up. So that starts to trigger conversations, well, is this a direct variation? Now, a direct variation, we want to be able to talk about variables. We want to talk about, in this case, pounds of candy and cost, but in other problems, we're going to be talking about other variables. So we want to talk about these quantities more, we want to be able to talk about these quantities more generally. So what I'm going to do is introduce a variable. I'm going to let P represent pounds of candy. So every time I incorporate this letter P, it is representing some amount of pounds of candy. And I also want to let C equal the cost in dollars. So again, when I'm talking about the cost, and I want to talk about it generally in this situation, I can use C, and that represents some amount of cost. If you know, and if you are told that two quantities have a direct variation, so if I say there is a direct variation between pounds of candy and cost, all that is telling you is if you take the ratio of cost divided by pounds, it will always reduce to the same quantity, or reduce to the same value. So if you take, and I'll say that again, if you know there's a direct variation between two variables, then when you consider those variables in a ratio, that ratio will always reduce to the same quantity, and this quantity we call the constant of variation. Constant of variation. And you could actually if you wanted to use P divided by C, that would also be okay. The ratio doesn't matter which way you write it as, C over P or its inverse, P over C. If you are taking two instances of cost in pounds and you write them as a ratio, they will be reducing to the same amount. Now I can go over here and just show you that there's a direct variation between pounds and cost, because if I do that for each one of these, if I take the cost and divide it by the number of pounds, right? If I take cost and divide it by pounds, what do we get for each one of these? Well, we get 450 divided by 1, which is 450. We get 9 divided by 2, which is, again, 450. 1350 divided by 3 is 450. And 18 divided by 4 is 450. So you can see here, when you take the ratio of cost to pounds and you consider all of these instances, they all reduce to 450. And what is that? Well, it's a instance of pounds, or cost of dollar per pound. So it's actually this 450, we saw this earlier in the course. This is the constant of variation. It is the dollars per 1 pound. So once again, if you know two things have a direct variation, then all it's saying is when you take a ratio of those variables, they will reduce to some constant. If you take 1 divided by 450 and you actually you do an inverse of this, you'll get the same thing, but that constant of variation in this case would be 0.222 repeating. So why is this any different? Why do we need to consider this? Well, it's because this relationship here can be rearranged as a function. So if I know two things have a constant variation, so C and P have reduced to the same quantity, or always that quotient is equivalent to some constant, then you can, if I want to, and I'm going to, rearrange this for C. So I'm going to multiply both sides by P. So if I multiply both sides by P, I get C equal to K times P. This is an equation. It's a little bit different than what we saw up above, where we have a ratio equal to some constant. This is what's called a function in this case, where we have the cost as a function of the pounds of candy. And this is what is typically memorized by students as the general form of a direct variation. And it's just directly from what we saw over here. It's directly from rearranging this idea of ratio. So what is the constant of variation in this example? We already found it. We know if there's a direct variation between two quantities, costs and pounds in this case, then if I take an instance of cost and pounds, so in this case, if I take $9 and divide it by 2, what do I get? I get 450. So the constant of variation is 450. Students also tend to plug in, they see, okay, there's a constant of variation. I know there's going to be an equation that I can find where one variable cost, or P, depending on how you want to set it up, will be equal to the product of the second variable and this constant. It's just a rearranging. So now if I plug in the cost of 9 and the pounds of 2, and I consider solving for this constant of variation, you'll see we're going to get the same thing. We're going to get 450. What that's telling me is I can rewrite this situation. The cost is equal to $4.50 or 4.5 times P. This is what we will be doing this week and in the coming weeks as we talk about critical care and titration. We are using the fact that the relationship between these two quantities, costs and pounds, reduces to the same amount. We're using that to write an equation. So we're just taking that ratio, rearranging it so that we can write it as almost like a formula. So this constant of variation is 4.5 in this example. And what is the other name that we've seen? This is just the invariant multiplicative factor that we saw in week 2, where we took and always were reducing. We saw that if two ratios were equivalent, they were being reduced to the same invariant multiplicative factor. That's what we saw. Now, this might be a lot of information. You might be saying to yourself, why are you making this so difficult? There's got to be an easier way to approach these problems. The reason why I am taking this approach is to show you how this direct variation is just a kind of a reworking of what we already saw in this course. If you know there's a direct variation, you can write the variables as a ratio and just rearrange it as this equation. And this is going to be really important when we consider critical care and titration. Let's look at a few examples. In this example, we are told a cashier earns an hourly wage. When the cashier worked 18 hours, he earned $168.30. Knowing that there is a direct relationship between the hours worked and the money earned, what we want to do is to explore this variation, this direct variation, by drawing a table to illustrate this situation. We want to find that constant of variation. We want to write an equation describing this situation and then use that equation to address this question. How much will the cashier earn if he works 25 hours? So a lot of things are going on here, but the first thing I want to be able to do is to be able to talk about the quantities in this situation generally. So I want to introduce some variables. And I'm told there's a direct variation or proportional relationship between hours worked and money earned. So let's let H equal the hours worked, and let's use M for money earned. And we already know the hours worked is going to be in hours, so money worked is going to be in dollars. So now we can use H and M to talk about the relationship between these two quantities. So I'm going to draw a table just very briefly, and I'm going to consider some hours and the money earned. And I'm told one instance of this relationship. So I know that when the cashier worked 18 hours, and we know H is in hours and M is in dollars, when the cashier worked 18 hours, he earned $168.30. We are told there is a direct, also proportional relationship, those are synonymous, between these two variables. So what that tells me is that the ratio of hours to dollars and its inverse, so dollars to hours, that ratio needs to hold for all other instances of these two variables. So if I'm just thinking here, knowing what I know about equivalent ratios, I know that, let's suppose this cashier worked twice the number of hours. So if he worked 18 hours, that would be, or 18 hours times 2 is 36 hours. Then he would have earned, knowing what I know about direct variation, in this case equivalent ratios, $168.30 times 2, he will have earned $336.60. All right, so all I'm doing here is just filling in a little bit of a table. I can do the same thing by multiplying by 3. So suppose he didn't work 18 hours, but he worked times 3, let's say 54 hours, so 18 times 3. Then I know this individual will have worked 18 times 3 hours, so the amount of money he earned will also be multiplied by 3, which in this case is $504.90. All I'm doing here is just creating a short table to illustrate that I know what it means for two quantities to have a direct variation. It just means this ratio needs to hold. It needs to reduce to the same amount. So that's all I'm doing, is just drawing a table to illustrate this situation. Find the constant of variation between these two quantities. I know that a direct variation, if you consider the ratio between these two quantities, so if I take the ratio of the money earned and divide by the number of hours, that needs to hold. That needs to equal some constant, which I'll call K. So in this example, I know $168 was earned, $68.30 over 18 hours. So when I do that, 168.3, and I divide that by 18 hours, I get 935. So my constant of variation is 935. And you'll find that if you take the other two ratios that we found here, 336.6 divided by 36, that will also reduce to this quantity. 504.9 divided by 54, that will also reduce to this quantity. That is the constant of variation. So we want to model this situation with an equation. So I'm going to bring this up here. I know, once again, that m over h is going to always reduce to 935. That's what I just found. So all I'm going to do is rearrange this. M will equal 9.35 h. That's it. That is really it. You're just finding what do the ratios always reduce to, writing that, and rearranging it. So now you have a formula. You have a formula that you can use to address other questions. So let's address this final question. Determine the amount of money the cashier will earn if he works 25 hours. So in that instance, I know H is equal to 25 hours. So if I plug that into my formula, I will get M equal to 9.35 times 25, right? And if you take that product, you will get M is equal to 233.75. So $233.75. I want to show you a shortcut in this example, and you're probably going to be angry with me, but I want to show again that there is another way to think about this problem. If you're told, and it's once again knowing what a direct variation is, if you know there's direct variation, you know one instance of the money earned divided by the hours will reduce to some constant. But you also know that some other ratio of money earned divided by, in a respective number of hours worked will also reduce to that amount. This is just a proportion. And in this example, we could have solved this final problem. We could have addressed this final problem using a proportion, knowing that in this example, the individual worked 160 or earned $168.30 in 18 hours. We want to know how much money will he earn if he works 25 hours. So if we solve this proportion, we will get, if we solve that proportion here, we will get 233.75. So if you know there's a direct variation between two quantities, you can solve that question. If you're just asked to address the question, you can solve that using a proportion, and that's perfectly fine. The reason I'm asking you to draw a table, and the reason I'm asking you to find this equation that models this situation, is because this is going to be important for us next week when we talk about the variation between the dose and the rate in titration and critical care problems. So that's why I'm having you consider a table just to be able to generalize the information, think about a ratio in terms of that constant of variation, find an equation. We have one more example. I know this video is getting a little long. If you want to pause the video and try the problem on your content guide, go ahead. I'm going to jump right into it now. We are told that the dose an individual is ordered directly impacts the rate in which the patient is receiving the medication. All we're saying there is there's a direct variation between the dose and the rate. So the dose is in micrograms per minute and the rate is in milliliters per hour. Suppose when a patient is receiving medication at a rate of 75 milliliters per hour, she is receiving a dose of 12 micrograms per minute. I once again want to just very quickly draw a table, find that constant of variation between the variables, and model this with an equation. Once I have that, I can address this question. What's the pump need to be set at so that the dose is increased to 20 micrograms per minute? A lot of things going on here. So I want to just very quickly introduce variables. So let's let D equal the dose, and that dose is going to be in micrograms per minute. And let's let R equal the rate, and that rate is being addressed in milliliters per hour. I want to draw a table using this idea of dose and rate. And this can just be very quick. It doesn't need to be anything crazy. And I know in this problem, when the patient has a dose of 12 micrograms per minute, she is receiving that medication at a rate of 75 milliliters per hour. So knowing that this is the relationship between these two quantities, I can use what I know about equivalent ratios to find other amounts. So if I take 12 times 2, I get 24. If the dose doubles, then the rate will double. That will be 150. If the dose triples, so times 3, I'll have 36 micrograms per minute. The rate will also triple. So if I multiply that times 3, I get 225. So again, just illustrating this is how this ratio is holding with various instances with these two quantities. So I know there's a direct variation. Let's find the constant of variation. I know that the ratio of the dose to the rate or the rate to the dose, either one you want to do is fine. I know that's always going to reduce to the same amount. So I'm going to use this idea of D divided by R. And you could do R divided by D if you want. We know that that's always going to reduce to the same amount. So I know 12 was one instance. When the dose was 12, the rate was 75. What is that? How does that simplify? So if I put that in my calculator, I do 12 divided by 75, I get 0.16. So what that's telling me is that the ratio of the dose divided by the rate will always reduce to 0.16. That's the constant of variation. So if I rearrange this situation, if I rearrange this formula, the dose can always be found by taking 0.16 times the rate. This is the equation that I'm looking for. The dose can always be found by taking 0.16 times the rate. So I drew a table just to illustrate I know what it means to know what's happening with this relation, or these two quantities, dose and rate. I know if there's a direct variation, they'll always reduce to this constant. So I found what that constant is, and I could have done that by plugging in 150 divided by 24, 225 divided by 36. They also would have given me this quantity of 0.16. And I use that, rearrange that here. I know the ratio will always equal that, so I find my equation, and now I can answer this question. What should the pump be set to if the patient's dose is increased to 20 micrograms per minute? So if the dose is equal to 20 micrograms per minute, what I can do is plug that into my formula. So remember, the formula is D equals 0.16 R. So I'm going to plug 20 in for D. So I get 20 equal to 0.16 times R. So I'm just going to solve this for R. So 20 divided by 0.16, you get R is equal to 125. So the rate would be 125 milliliters per hour. Once again, just to check your work, if you wanted to check your work, you can try to set up a proportion. 12 micrograms per minute over 75 milliliters per hour needs to reduce, or if the dose is increased to 20, what is that equivalent milliliters per hour? So if you cross multiply here or consider any of the other methods that we learned, you should get 125. But again, just in these problems, we want to introduce variables. We want to find that formula, that equation, so we can use it for future problems and not have to set up a proportion all the time.